All right, so today is an introduction to logarithms and a little bit of graphing. So we'll grab the graphing calculators out in a minute to do the graphing also. So a couple of things that you need to know about logarithms. These are their basic forms. You have a number raised to a power equals a number. And we can rewrite that as log base b to the a equals x. So a logarithm just answers the question, what exponent is required to go from a base of b to reach a value of a? And maybe this is kind of hard to understand. I'm going to show you a little method called the circle method in just a minute. But what we're really doing is we're taking this form of an exponent and we're writing it as a logarithm today instead, or we're writing the logarithm. Or we're taking the logarithm and rewriting it in exponential form. Really what a logarithm is a exponent written in a different method, okay? So I like to teach what's called the circle method. If you see what happens here, do you see how we draw a circle around to remind us what we're doing here? So if you have something that's log base b of y equals x, you're going to rewrite it, and this is hard to see over here. But on this side over here, that says b to the x equals y. So let's see how that circle worked. We started at the base, we went to the other side of the equal sign, and then we came back around to the number that was attached to the base. So it was b to the x equals y. Do you see how the circle works? So if you follow this circle around, it's going to help you rewrite your logarithms. So right here on number 1, if we're going to rewrite this, we would start here. We're going to go to there and then back around following our circle to here. So how do I rewrite this logarithm as an exponent? Ooh, start with the 3 though. So 3 to the second equals 9. Is that actually a true statement? 3 to the second equals 9? Yeah, 3 squared equals 9. So do you see how logarithms work? This was base 3, this one's base 8. A logarithm can be in any base. When we talk about having the word log there without a base written there, it would be log base 10, which is our normal number system. You guys know that we have a base 10 number system, right? Because we use what numbers? 0 to 9. How many numbers are there in 0 to 9? 10. So log base 10. Binary or computer code is written in base, anybody know? 2, because you only use zeros and ones. Okay, so do you see what the base is telling us? It's really telling us how many numbers we're using in that number system. So if we were looking at this would be some kind of a number system with a base of 3, which is why it's 3 to the second power, because we're talking about 3s. All right, help me rewrite number 2. How does it go? Start here, do your circle around. Yep, 8 to the 0 equals, is that a true statement? Yeah, that's a true statement, right? So now the question is, can you go backwards? We know we're going to have a log. We know we're going to have a base and a number. We know it's going to be equal to something. So going backwards from here, if the base became the big number, what's the base going to be over here? 10. Where's the 3 going to go? Yeah, over here on the other side of the equal sign. And what number comes back over here? The 1000. You can always just check your work. If you can't remember, you're like 10 to the third power equals 1000. That's what it said over here. So this way we're just going backwards. Now I want to show you something here. Does the circle still work? Yeah, right. 10, 1003, 10, 1003. Did you see how it tells you the order to write it in? Okay, so thinking about that, how you're going to rewrite number 4 is going to be log base what? 5 of what number? Oh, 1. So remember how the circle works? So it's this, and then that, and then this, in that order on the log, right? So that, it was 10, 1000, and then 3, 10, 1003. So here it's going to be 5, 1/25, and -2. And again, you can just check that. Does 5 to the negative 2 equals 1 over 25? And that does work that way, so we are going to just leave it like that, okay? So these say to solve on your calculator, but your calculator doesn't do base 4 and base 2. Oh, I'm sorry, this says without a calculator. So we're going to rewrite these the way that we had rewritten just a minute ago, and we're going to solve them without a calculator. So how is this going to be, what's this going to be equal to when I rewrite this? What's over here on the side for it to be equal to? You don't know, right? So could we call that like an x? Could we say that this would be equal to some answer? Is that okay if we call it x? So we would write 4 to the x power equals 64. And you really just have to find the power that we would raise 4 to get 64 for your answer. So what power do we raise 4 to get 64? 3, yeah, it's 3, because 4 times 4 times 4 is 64. So your answer would be 3. I like to just set them equal to a variable, so when I think about my circle, I can remember what I'm doing here. So this is going to be 2 to some power equals 1/8. You guys agree with me? That's the way the circle would work, right? 2 to some power equals 1/8. So what's the power you're going to raise the 2 to? How do you get the 8 to go to the bottom of the fraction? It's got to be a negative power, right? So think negative powers and just punch them in your calculator till you figure it out. It's negative 3, yeah. If you do 2 to the negative 3 power, then you would have 1 over 8. All right. So somebody just shout out to me how I'm going to set up number 7. What's it going to look like? To some power equals 2. Now this time we're going backwards. So going backwards would be like taking a root of it, right? Which would be a fractional power. So if you're going from a bigger number to a smaller number, you're going to have to think fraction power, which is also the same way as thinking of a cubed root or a fourth root or a root of, what do you think it is? 1/16? I think that you divided there. Think powers. I like to kind of go backwards and say, well, how would I get from 2 to 32? It would be 4. 4? 5. Right? Is it 5? Because 2 times 2 is 4, times 2 times 2 is another 4, so that would be 4 times 4, which is 16. Times 2 one more time is 32. So it's not going to be the power of 5, but what about the power of 1/5? Punch that in your calculator, you guys, and see if 32 to the 1/5 power is 2. Yeah. It is, right? It's 1/5. I don't, actually. I was just looking. You might go down to the office and ask Andy for some if you want.
I'm too lazy. I'll do it later.
Hey. Here, I do have a napkin.
That'll do it. Thank you.
All right. Did you go ahead and do the last one for me? Because it's like set up and ready to go. You'd have 2 to some power equals 2 to the 8th power. That's pretty easy, right? What's x got to be? 8. Yeah, x has to be 8. So you'd have 2 to the 8th equals 2 to the 8th, which makes a true statement. Okay. So again, what we're doing today is we're just trying to figure out what logarithms would be equal to without using a calculator. You guys, I'm not going to lie to you. You could try to punch this in your calculator, but you don't know enough rules to yet. Your calculators won't do logs in base 2 or base 32 or base 4. So you have to rewrite it in order to get it to simplify. In a couple more days, I'm going to teach you another rule. It's called the change of base formula that's going to help you punch it in on your calculator. Okay. All right, so we've already talked about some of the logs that we use. The common log would be base 10. That would be in our number system. The natural log would be base E, which we learned about E the other day. And it stands for ln. So if you have a base E you could totally change it to an ln and make it work on your calculator. And then the other most common logarithm is a base 2 for binary. Okay, and there's no special symbol for it. We just have to do it by hand still. All right, so if we have a log base 10 or a natural log, which is base e, we can simply plug them in on our calculator and solve them. So everybody find the log key on your calculator, and it actually says log. Did you find it? It's right there below the second key, right? So you're going to do the log of 7. So hit log, hit 7, and what'd you get when you do that? Yep. And it says round to 3 decimal places, so we're going to stop right there. Okay, the natural log this time, the natural log is the key right below it, the ln key. So this time you're going to do the ln of 0.25. And you get negative 1.386 if we're rounding to 3 decimal places. You're going to do the log of negative 3.
What's the difference between ln and log?
Okay, the log, the log is in base 10, and the ln is in base e, which is the 2.7 number. So those are the two most common logs that we use, but the log, the log one, is in base 10. I did. What happened when you did the log of negative 3?
That's a good question.
Yeah, it gave you a domain error, right? And anytime we get a domain error, we know it's undefined. It means it's not possible to do. Okay. And then that last one, the ln of 50, 3.912, thank you. So calculator work if it's written in log or natural log form. Okay. All right, so it says earlier we estimated the value of x. If we had e to some power equals 50, we could totally just approximate this, but it says let's write this in log form. So if we're going, this was actually, do you remember what we just said about the natural log? The natural log is in base e. So we don't normally show the base e there, because we don't have to have it there, but we're going to rewrite this so that it's in natural log form. And they told us that it was approximately equal to 4, that x was, so it was a 4 up here. So think in circle here, we'd have, because the circle still works on any kind of logarithm, so we'd have the ln base e of 50 equals 4. When you rewrote it in a logarithmic form, again, because the circle is the way that that's going to work. And again, if you have something in base e, you're going to write it as a natural log. Otherwise, over here, if you notice, depending on what the base was, the logarithm was base 32 here, so 32 was the base of your number over here. But if we would have had one that just said log of 2, log of 2 would have been in base 10, because if we have the log going on there, it's naturally in base 10. So don't forget that. The natural log is always base e. We don't show the base e there. It's just written as the natural log. Okay. All right, so it says let's take a look at some of the graphs here. The log graph looks like this. The natural log graph looks like this, so they're very similar in the way that they look. Okay. If we wanted to graph their inverses, the inverse of the logarithmic graph would be the 10 to the x, because a log is in base 10. So these are inverses of each other. Okay. Which again, it shows an inverse is the reflection over the line y equals x. And then the inverse of the natural log would be e to the x. And I think the biggest giveaway to remind you of what the inverses is when you look on the calculator, the inverses are always on the same key. So the log and the 10 to the x are on the same key, and the natural log and the e to the x are on the same key. So those are the inverses of each other. Okay. We can move a logarithmic function left, right, or up or down just like we did every other function. A stretches it. H is a horizontal shift, meaning left or right. Okay, is a shift up or down. Okay, so if we just used our natural log graph up here, which is this one, this is the natural log, this is the e to the x graph. If I use my natural log graph right here, what's this graph asking me to do to it? It's attached to the x inside with subtraction. So left or right? That would be moving that natural log graph to right 3. So instead of crossing the x-axis at 1, where's it going to cross the x-axis at? Over at 4, right? And then you're just going to regraph that same kind of graph that it was. Okay. What's this one asking you do to the natural log graph? Up, down, left, or right? Which one is it? It's up, yep. So instead of crossing at 1, you would move it up 4. And your new natural log is coming up through there like that. So it really is just shifting them like we've been doing on all of our other graphs. Okay? So the same thing on these next two. We're shifting them left, right, or up or down. On this one, we even have the negative out front, which flips the upside down. It says to show the asymptote, which is really that line that it doesn't cross, which in this case would be the y-axis. In this case, it's probably the number 2 or 1 right over here. So you're going to graph them, you're going to show the asymptote, you're going to state the domain and range. So I'm going to help you just sketch them really fast. The plus 1 is left 1, and the minus 3 is down 3. So instead of crossing at 1, 1, which is where it crossed, you went left 1 and down 3, which is where your new graph is going to be coming through. So you're something like that.
You know it crossed at 1, 1.
Well, it started crossing at 1, 1, but I have to move my crossing point to left 1 and down 3. Right? So I moved it left 1 and down 3, which is where it should be crossing now. And then this one is up 2, but upside down. So it was crossing here at 1, 1. I'm going to move it up 2 from there. Instead of coming this way like this, it's got to be going the opposite way. So instead of being, say I was over here at like 1, 1. Here, I'm going to just graph it for you on the graphing calculator so you can see what it does. Negative ln of x plus 2. It comes down through that point instead of up through that point. So you're just like this. Okay. Then you can use your graphing calculator to help you do domain and range and asymptotes if it asks you for those on your worksheet.